Now that we know all about analyzing sinusoidal steady-state circuits, and we've taken the time to determine the Thevenin and Norton equivalent circuits, it may have brought some memory of the concept of maximum power transfer. It is possible, however, that there is some question in the back of our mind as to how to handle power determinations involving sinusoidal sources. What do we mean when we say power? Are we talking about power at a specific instance in time? Are we talking about average power? Or are we talking about something completely different? We know that electric power is the product of voltage and current, but now that we have sinusoids and phase shifts, we're going to get drastically different results for seemingly similar situations. For example, since a phase shift of 180 degrees is the same as multiplying a cosine function by a negative sign, the phase shift can change something from looking like it is absorbing power to looking like it is supplying power. Or if the voltage and current are shifted by 90 degrees from each other, the power will average to zero. Would that mean there is no power available for an inductor? Or possibly, if the power averages to zero, does that mean electricity would be free? Clearly, there are many questions to answer. Power is always a very important practical concept. Even for a component as simple as a resistor, we know that absorbed power is turned to heat. Too much heat can cause a significant problem, especially if we are not trying to start a fire. Another obvious practical concern is that power usage costs money. The power company charges us based on the amount of power we use and how long we use it. If we run a 1,000-watt heater for 1 hour, we will be charged for 1 kilowatt-hour of energy. How does a time-varying signal affect power determinations? We will need to develop a few concepts. We remember that power is voltage times current. In a direct current circuit, that is the end of it. But when time is involved, we need more information. Are we looking for the power at a specific time? That would be the instantaneous power. That can be important for situations where we need to know the maximum power that's going to be present. More often, we need to know something related to how much heat is going to be generated. But mathematically, the average power changes depending on whether the voltage and current are in phase or out of phase. In these graphs, the current is shown in blue, the voltage in red, and the product of voltage and current, the power, is shown in green. When the waves are in phase, the power is a cosine wave that is shifted up so that it is always positive. When the current and the voltage differ by 90 degrees, though the amplitude of the power looks identical, the power waveform is an inverted sine wave that would average to zero. The extremes of this are a little interesting. If there is no phase difference between the voltage and current, the average power is 1/2 times the peak of the voltage times the peak of the current. We'll have to take a look at that factor of 1/2. In addition, we might notice, as the phase angle between the voltage and the current is 90 degrees, there is no average power. Furthermore, if the phase between the voltage and the current increases to 180 degrees, the average power is negative. Does that mean that the passive components can turn into a source? Maybe. We clearly need to develop some new vocabulary, concepts, and methods to discuss power when dealing with sinusoids. Let us take a closer look at the instantaneous power in the case of sinusoids. If we look at a voltage with a magnitude of Vm, an angular frequency of omega, and a phase angle of theta, and look at a current with a magnitude of Im, the same angular frequency omega, and a phase angle of phi, but we can substitute these expressions into the power equation. If we rearrange these, we can pull out one of our favorite trigonometric identities to simplify the expression. In this case, we end up with an expression for power that has a term with 1/2 times the magnitude of the voltage and current times the cosine of the difference in phase angle between the voltage and current, and another term that has the same magnitude and a cosine term that still has an angular frequency dependence. That means there is a constant term that is dependent on the difference in phase angle between the voltage and current. And there is a time-dependent term at twice the angular frequency of the original signals. We saw that in the graphs we just looked at. When the difference in the phase angle between the voltage and current is 0, the cosine function is 1 and the power wave is shifted up by 1/2 times the product of the magnitudes of the voltage and current. If the voltage and current are out of phase by 45 degrees, that shift is reduced by a factor of 1 over the square root of 2. And when the voltage and current are 90 degrees out of phase, the cosine of the difference is 0, so there is no shift, and the average power is 0. On the other extreme, if the current and voltage are 180 degrees out of phase, the magnitude of the shift is 1/2 times a product of the magnitudes of the voltage and current. However, this time it is negative. The constant term can be called the average power, since the variable portion centers around it. If we want to approach this from a little more formal perspective, we can remember that the average of a periodic function is 1 over the period times the integral of that function with respect to time over said period. We can integrate each portion of the sum separately, with the first portion of the sum not having a time dependence, and the second term of the cosine function that will average to 0, so we end up with the same expression. An even more amusing thing might be to look at this from the perspective of phasors. Starting with the same power equation and the same time-dependent voltage and current, we can convert the current and voltage to the phasor domain. If we look at the product of the voltage and current in light of what we have done, we see they do not give us the same result. So we are going to have to make some modifications to our power calculation in the phasor domain. In order to obtain the correct results, we can look at the product of the phasor voltage times the complex conjugates of the phasor current, and 1/2 times the real part will be equal to the average power. Now, before you accuse me of sneaky, backhanded, sloppy proofs, never mind, this qualifies. But it is more fun than a formal proof. If you want a formal proof, there are many books that will provide it. We are still left with 2 questions. First, why is there a factor of 1/2? Second, if the average power is the real portion of the phasor product, what does the imaginary portion represent? I think we should start with a factor of 1/2. In a purely sinusoidal system, both the voltage and current will average to 0. Even though these quantities average to 0, that does not mean the effect they have averages to 0. If we were to connect an inductor, one that has a very small resistance, to the wall outlet, the voltage and current would be 90 degrees out of phase, and the voltage, current, and power would all average to 0. Yet the circuit breaker for the wall outlet still trips. If the average of everything is 0, what is it that had enough of an effect to trip the breaker? This is where a discussion of the root mean square of a quantity is useful. In general, root mean square is a statistical term. When we apply it to a continuously varying electrical quantity, it results in an effective value. When we say the root mean square value of the voltage, we are talking about a voltage that represents the AC voltage in such a way that it would provide the same average power as a DC voltage of the same value. So when we say the wall voltage is 120 volts RMS, it is saying more about the effect of the voltage than the actual value of the voltage. The actual expression for a 120 volt RMS 60 Hz voltage is V of t equals 170 cosine of 377 t volts, but it delivers power as if it were a 120 volt DC signal. Here we have the average value of an arbitrary function x of t, in which we have made x of t equal to an arbitrary cosine wave with no phase shift. If we integrate and evaluate the average over a period, we get 0. However, if we calculate the root mean square of the same function, we have a bit more challenging of an integral. We can use a trigonometric identity to change the cosine squared function into 1/2 plus 1/2 times the cosine of 2 omega t. Setting up the sum as 2 separate integrals, we have the integral of a constant with respect to time and the integral of a cosine function with respect to time. Though this looks like a mess, when we evaluate the function, the period cancels for the term on the left and the sine function evaluates to 0. We are left with the square root of the square of the magnitude over 2. In the end, the RMS value of a sinusoid function is the magnitude divided by the square root of 2. Now we have an explanation for the factor of 1/2. If the RMS value represents the ability of the signal to deliver power, then the RMS value of the voltage and the RMS value of the current should be used to calculate power. If we put the peak value over the square root of 2 in for the voltage and current, we end up with a factor of 1/2. Returning then to the sneaky backhanded derivation. If the average power is the real part of the phasor voltage times the complex conjugate of the phasor current, there must be some quantity that includes the imaginary portion of it. When we include both the real and imaginary parts, we call this the complex power. I know, it's so creative. So we have the complex power, the real power, and something we're going to call the reactive power. Mathematically, all of these have the same dimensions. However, to help our simple brains keep track of them, we refer to them with slightly different terms in units. Power is voltage times current. When our quantity is complex power, S, we use volt amps for the unit. P is the average real power, so we still use watts. Q is the reactive power, and this is measured in volt amps reactive. So what do each of these quantities mean? Maybe the best way to get an idea is to do a quick calculation. If we assume a simplified model of the core of an induction motor at 60 Hz, the impedance might be something like 10 plus J100 ohms. If the voltage across the core is 110 volts RMS with no phase angle, the current will be 109 amps RMS with a phase angle of negative 84.3 degrees. If we calculate the current through a load using an RMS voltage of a sinusoid, the current will also be an RMS value. Since both the voltage and current are RMS values, the complex power is the voltage times the complex conjugate of the current, which yields about 12 plus J 120 volt amps. That means there is 12 watts of average power dissipated by the motor and 120 volt amp reactive exchange between the source and the motor. We are likely still in a place where we have more questions than answers about this, but at least now we can start asking some interesting questions. For example, if the power company charges for kilowatt hours, are volt amps reactive free? Or how about if the current I'm drawing from the power line has a big phase shift, does that affect the voltage and current for other things connected to the line? We'll have to look at those questions later. For now, we have looked at the difference between instantaneous and average power. We have seen that the phase angle between the voltage and the current has a great effect on the effective power. We define some quantity, root mean square, that helps us interpret periodic signals. And we define something called complex power that has a real part measured in watts and an imaginary part measured in volt amps reactive. Beyond that, we'll have to wait until next time. For now, go out and make it a great one.